Hey, what's up? It's your old pal, Mr. Cook, and we're working on this AP Calculus BC Semester 1 final exam review. Number 27 and 28, they're like rational functions. When I work on rational functions, I always think to try to use, like a U sub if I can, okay? But that's most cases if I see a rational function. But sometimes there's some problems where it is very obvious that you've got to use partial fraction decomposition and then a U substitution. It just makes things a lot easier. Okay, let me give you an example. Like if I go to number 28 real quick, right? I can spot really quickly that this is not going to be a U substitution because if I took the derivative of the bottom function, it's not going to be 1. And that's what I would need. I would need it to be the numerator or like a multiple of the numerator for it to be just a simple U sub. Like if I saw, what's the derivative of x squared minus 5x minus 14? It's 2x minus 5. If I saw that in the numerator, hey, I would use a U sub like immediately. Or if I saw a multiple of it, like maybe if I doubled that, so 4x minus 10, because 4x and 10 are both divisible by 2, so that'd be a 2x minus 5. And then you can see that that's the denominator of that, so I would use a U sub. Something like that. Like that would be a U sub, okay? But when you have rational functions, like a polynomial on the top, a polynomial on the bottom, if you can factor the bottom part, there's the potential for you to be able to use partial fractions. And if the bottom part is factorable and the top part, the numerator, is just a constant, 100 times out of 100 times you should use partial fractions. Or I shouldn't say that because there might be some special circumstances, but most times you use a partial fraction decomposition. That's just so that's like my mentality, how I see the problem, right? And again, I've seen a bunch of these problems. And this just screams partial fractions to me because number one, it's already factored. It's quadratic and it's already factored. And on top of that, it's like a constant in the top. And that's all the stuff that I have to work with. This is like an ideal situation to do partial fractions. So how do you do partial fractions? The idea is to split this one fraction into the sum of, in our case, it's going to be 2 fractions. Okay, so we're going to have x minus 4 in the denominator of one fraction, and then x plus 5 in the other fraction, okay? And we don't know what the numerators are yet, so we'll just call those a and b for now. And we're going to try and figure out what those are. So the way that we do this, the algebra behind it is, the way that we add fractions. It's kind of like the reverse of adding fractions. If I have 2 fractions, like 1/2 and 1/3 or something, or, whatever, 2/4 or something like that, okay? If I want to add fractions together or subtract them, I need to find a common denominator. So, you might have been told, hey, find the least common denominator and all this other stuff, right? Well, what you can do instead is just take the other one's denominator, like 3, and multiply it, and then numerator and denominator. That's how you can just kind of spam the process of finding a common denominator and then take the other one's denominator and multiply that in the numerator and denominator of that fraction. Then what happens is when you do this process, you just take one's denominator, multiply it in the numerator and denominator of the other one. Then you get, an equivalent fraction with common denominators. And then it's really easy to add this stuff together. You just, you keep the denominator the same, so 6 stays the same, but then you add those top numbers together, 3 and also 8, okay? And I'm going to leave 6 as 3 and 2 for the purposes of showing how we're going to use partial fractions in a second. Okay, so here's the problem, all right? So 3 plus 8, we end up with 11. So imagine that this part here is equivalent to where we start. And we need to make our way back to our original fractions, okay? So that's how we need to get there. So we're going to take these steps here to get to, that goal, okay? So the first step that we do, you got to kind of think about it backwards. It's weird. It's like you have a fraction. How do you split it apart into 2 fractions? You first have to understand the factors in the denominator, okay? And that's the whole process of factoring the quadratic. You find those numbers, okay? Then the next thing that we do is this middle procedure right here, where we take one numerator, right, one of the denominators that we're going to use, and multiply it in the top and the bottom for both fractions. So that's like kind of the purpose of this. We kind of like imagine that we've already split the fractions apart. So we've got these two different denominators, and we just do that like little middle part where we multiply the top and the bottom denominators together. It's going to be very much the similar process, okay? So here's how we find out what a and b are going to be equal to. We start off with, a over x plus minus 4. This is our goal, that we want to make it look like this, fraction, okay? X plus 5. And then we get a common denominator between these two. So I got to take this one's denominator and multiply it in the top and the bottom. Because, right, if I multiply it in the top and the bottom, it doesn't really change the fraction, right? It just multiplies it by 1. So that doesn't change it at all. And then over here, we're going to multiply by the numerator and the denominator. And here's what this ends up being. All right, so the top part, like here, just becomes a times x plus 5. And then this part becomes b times x minus 4. And they both have the same denominator now, so that's just going to be this common denominator that we have, x plus 5, x minus 4. And then these two numbers are going to add together, right? So I'm going to put a plus right there. Okay, so I claim that this fraction that I've just created right here is actually the same as this like beginning fraction that we start off with, okay? And the way that I can make them the exact same, if you look closely, is by finding out what the a and the b values are here, because those are the only unknown values that we have. And I'm going to tell you right now that we're going to be able to solve for those, with this idea. So if these two fractions are equal to each other, okay, then how do we solve for a and b? Well, the denominators are already the same, so we actually can just sort of like ignore those parts, all right? Just ignore them. Because if, they have the same denominators, the only thing we're really interested in is the numerators at that point. Okay, now you can actually use any x value you want to solve for a and b. All right. So like if I set x equal to 0, I could get rid of the x part here and here essentially, and create a system of equations. Like, so watch, if I set x equal to 0, then I get 1 is equal to 0 plus 5 is 5, so 5a plus, and then 0 minus 4 is minus 4, so negative 4b. And that's like one equation that I could get. And if I use a different x value, like x is equal to 1, let's say, then I plug in 1, here and here. So I get 6 times a, and then and if that's a 1, that turns into a negative 3. So negative 3b also is equal to 1. See, and this becomes a system of equations. You can solve systems like really, really easily, okay? But if we're strategic about the x value that we plug in, we can actually solve for a and b really, really quickly, okay? Because you can actually use any x's in here, because this is supposed to work for any x value, in the numerator. We actually will see that like these one values that we pick are exactly the domain restrictions that we have, but that's beside the point. So we're going to plug those numbers in, okay? These numbers that make things really, really easy. What number would be nice to plug in for x to get rid of that 5? If you said negative 5, that's right. If I let x equal negative 5, then that becomes, 1 is equal to, and then negative 5 plus 5 is 0. So 0a, which is 0, plus, and then if I plug in negative 5 here, I get negative 9b. So look at that. Like, this is a much easier expression. I can solve for b outright by just dividing by negative 9. So that means that my b value is negative 1 over 9. So that's the exact b value that I'd use over here, negative 1/9. And similarly, if I pick another x value strategically, so the x value that I'd pick maybe like over here, if I picked 4, that'd be really nice, because that would, cancel out or make 0 here and then get rid of the b value. So that's what I'm going to do. I'm going to plug in 4 for the next one. So I plug in 4 over here. 4 plus 5 is 9, so I get 9a plus, and then 4 minus 4 is 0, and 0b is just 0. So it's just 9a. 9a is equal to 1. That means that a is going to be equal to 1/9. So now, my a value is equal to 1/9. And now check this out. we've changed through this partial fraction decomposition. We've changed this fraction into the sum of two smaller fractions that are actually really, really easy to find an antiderivative of. These are two really basic U subs. So if you want to practice the U sub, you can. But if you're in my class, I showed you how to do these ones really fast. The 1/9 is just a multiple, so that goes out front. And then the antiderivative of 1 over x minus 4 is just going to be natural log of the absolute value of x minus 4 times the derivative of x minus 4 is just 1. So we're not going to add that part on. And then minus, and then we have a 1/9. And then it's going to be natural log of the absolute value of x plus 5. And then, we multiply that by 1 over the derivative of x plus 5 if it's a linear function, which would just be 1 anyways. And then plus c. And that's our finished answer for this problem. Okay, so now I've shown you a ton of steps, but it's actually pretty quick if you kind of just do them all sort of in motion, real fast, not stopping to explain everything. So 28, I'll show you how quick you can do it. So this one isn't even factored. So first things first, we try to factor our quadratic. If it factors, cool. We can use partial fractions. If it doesn't factor, then there's some other thing that you can do, and that's use completing the square with arctangent for the most part. It usually works out pretty well. So there we go. Factor, and then split the fractions apart, but you don't know what the numerators are going to be. So it's going to be a over x minus 7, b over x plus 2. And then we start our little partial fraction steps. Okay. So, you multiply this one's denominator over on the other one. So you have x plus 2 times a over x plus 2 times x minus 7 plus, then you multiply this one's denominator over on the other one. So it's going to be b times x minus 7 over x plus 2 times x minus 7. And then this is supposed to be equal to this beginning fraction, or I guess this one that's all factored. So 1 over x minus 7 times x plus 2. And notice that the denominators are the same, so you just kind of ignore those, except for the domain restrictions, obviously, but you can ignore them for the most part for solving purposes. There we go. All right, now pick some strategic x values, like maybe from this one, I'd pick x equals -2. So if I did that, I get 0a, and then plus, looks like -9b equals 1. So that means that b is going to be equal to -1/9. So I'd, put that over here for b. And then from here, I'd pick another x value. X would be equal to 7. That'd be really nice. So if I did that, I would get a times 9, or 9a, plus b times 0, which is just 0. So 9a equals 1, and therefore a is going to be equal to 1/9. And then, the rest of it's just simple U substitutions. So, yeah, just go ahead and do that. All right, so this is going to be equal to, let's see, this antiderivative. I'm going to use that 1/9 out front. And then 1 over x minus 7 turns into natural log absolute value of x minus 7 times the derivative, 1 over the derivative of the constant if it's, or the inside function if it's a linear function. And then plus, or actually minus 1 over 9 because it's a -1/9. And then natural log absolute value of x plus 2, and then plus c at the very end. Okay, so there's my finished answer. And to be honest with you, if you, worked on this problem, or you had to do this as a multiple choice question, that's probably just what we would have as a response. Okay, that's it for this video. I just wanted to do the partial fractions problems, and the next ones, probably do those 3 together because those are improper integrals. So that's where we're going to need limits. They take a little bit of time. So I'll just have a video for just those alone. Okay, hope you enjoyed this video. Hope it helped you out. If it didn't, go find your math teacher, your calc teacher, whatever you got, and ask them for help. I'm Mr. Cook. If you ever need my help, you can come and find me. I'm usually available in the morning or after school. I'm always willing to help, so come by, please. Okay, I hope to see you in the next video. Bye-bye.